dual space. So yeah, if I don't know if I remember everything. We have to look at the book needed. So dual space, but yeah, should be fine. So here, of course, the dual space concept is very important, and yeah, let us see. So dual space of a finite dimensional vector space. So first, one should be, if you are doing dual space, one should be very clear about the notion of linear functional, right? So that is the important definition. Okay. So may I ask, which book have you read this from?
It's Fredberg.
Fredberg. Okay. Name is linear algebra.
Yes. I have the book also. Mm,
Okay, no problem. Anyways, so it's fine. This Fredberg, I have not heard the name, so no problem. So, yeah. So first, let us define the notion of a linear functional. So definition of linear functional. Here, our vector space will be denoted by V, and V is over a field F. Okay? Over a field F. V over F. So you see, once we say this in a very crisp way, you see everything very simple. So linear functional is just
Linear transformation from V to F.
exactly the linear transformation from V to F. So F, and F is just linear transformation. So it's linear transformation from V to F, right? So this is all, right? And V star, which is the dual space,
Is
V
a
star,
collection of all the linear
exactly. So it's just a collection of all linear transformations. So it is basically this thing, okay? But yeah. So this is F, such that F from V to F is linear, and it is F linear, of course. I maybe I won't write F linear, I just write linear. Okay. So this is what the dual space is. The dual space is a space of functions, right? Dual space is a space of functions. Okay. Yeah, it's just a space of functions. But if you want to understand it a little bit more from a visual or maybe more concrete angle, then so what you do is you fix a basis, right? So fix a basis for V. Okay. So once you fix the basis for V, okay, write F with respect to maybe I should say fix a basis B. Fix a basis B. Right? B is a basis for n vectors, n-dimensional space we are assuming. Then you write F with respect to B, okay, and this is a matrix, right? So what will be the dimension?
dimension of the basis.
No, matrix. What will be the size of the matrix? 1 cross n.
If the basis contains N, yeah, N,
Yeah,
1 cross N.
it's a 1 cross n matrix. So it will be 1 cross n matrix. So it will just be a um, maybe I can just write as A F, right? And this is just a 1 cross n matrix. Okay. So when you fix the basis, then you get this thing, and then this. So after you fix the basis, then this just becomes the collection of all 1 by n matrices. Yeah. So the information is just this, or maybe I will write. Then you can see it makes sense. The information here on the left hand side is all encoded here as you fix the basis, and once you fix the basis, then all you get is this collection of uh, 1 by n matrices with coefficients in F. Yeah. And let me say one more thing, and then you can see F by this. So how is the relation? How is the connection? How is this connected? Because it's actually not equal. Yeah, I should not write because these are different things in that sense. But F goes to just this matrix of the linear transformation with respect to the basis. Now you see what is here. Any good?
F is a linear transformation, so we can take it as a matrix too.
Take it
So
as a matrix, no, but you can take it as a matrix only after you fix a basis.
yeah, the matrix is AF, right?
AF, but AF comes after. So AF is written with respect to the basis B. So if you don't mention what is the basis, one matrix doesn't determine one linear transformation. It can determine many linear transformations. That's
So
the
if beta if the basis is like v1 v2 v dot 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 vn,
mhm.
then what will be AF?
The AF will that AF will be a matrix, right? Yeah, and what will be AF? So AF will be uh, AF will be this, and it will be F of B1, F of B2, F of B. If you change the basis, the matrix will change. AF will change, right?
Yeah.
You agree that AF will be this? That you know?
Oh yes,
Because
yes, yes,
that's
yes.
like a rule. That's almost like a rule, right? Yeah. And of course, but yeah. So that's a very important thing that the matrix that you write for a linear transformation depends on a basis. Because when you give a basis, means I'm saying maybe too many words, but if you give a basis, then you get some coordinates. And when you have coordinates, then you can write matrices. But very simply, you can see the matrix will change if you change. Right? So all I'm saying is that you take a basis, then this just becomes a collection of matrices, all 1 by n matrices, right?
Hmm.
You agree
Hmm.
with this? Now,
Hmm.
now let us see if this helps to understand. So what I have in mind is to show first that this is a vector space isomorphism, okay? And then I want to say that uh, then I will try to say that given a linear functional, how do you visualize it uh, as a hyperplane? Okay? And then we will see that these linear functionals basically look like hyperplanes. And those are two things I plan. And then maybe I can talk about the double dual, three things. And then I can ask you if there is something that you want to understand about duals. From the book, you can see some theorem, something which that way you but more helpful, I think. Right? Yeah.
But I have
So
not done vector in isomorphism.
okay, but then you have to do now. Means it's okay. I mean, it's not a problem. So don't worry about it. Okay. Yeah. It's just a group homomorphism. Okay, almost. So vector space is also a group, right? That addition is a group, right? Addition and it's a group. So we'll show that. That's all. And then we can say that this scalars you can pull out at will. So let's see. First you see that V star is also a vector space. Okay, right? You agree with that? V star is a vector space.
Yes.
Okay. So V star is an F vector space. You can check all the vector space functions. In fact, if you take the collection of all functions from a vector space to a field, that also is a vector space.
What is F vector space?
F vector space, yeah, this maybe is a terminology, means that it's a vector space over F.
Okay.
With
Vector
F
space
as the
over
field.
F.
Yeah. It could be a vector space over something else also, right? Because it's something new. But we are emphasizing it. But as fact, I will not write it anymore because F is the only thing in the vector, so better to not unnecessary. So it's a vector space. So when it's given that it's a vector space, you would want answers to many questions like what is the dimension of this vector space and so on, right? So all those things. So okay, number one, let me write the questions. Actually, that's I think a good approach. Good to write the questions first. What are the important questions? The important questions is the what is the dimension of V star, right? Dimension of V star. This is the question. And yeah, what was I going to say? Yeah, what is the dimension of V star? And we also want to say what is a good basis? What is a good basis? Yeah. This is in quotes because it's not a mathematical term. We'll see that it's good or looks, then we can agree maybe.
Good.
Yeah. What is this is the game. This is the main game, right? What is a good basis? This is what you would have read in the book is a dual basis. Maybe if it's dual basis. That is very important. And all these things get automatically clarified once you develop the notion of vector space isomorphism. It takes a little bit of work, but it pays off very nicely. So, yeah. so this is a vector space, and the right hand side is of course a vector space. So right hand side means what I mean is just this, right? Just this. So I will write it more accurately. At first to explain, but more accurately, if I write, then I should write like this: that once the basis is fixed, means any basis you can take. Okay? Any basis you can take. I mean, if you don't want, you can take V to be Rn, and you can take basis as 1, 0, 0, 0, 0, 1, 0, 0, 0, and so on. So it's up to you. Any basis B. Once you fix that basis B, then this is just the same thing as M and F. Okay. Just imagine if the dual space is just okay. No, it's not M and F. It's 1 cross n. Right? It's even simpler. If this V star is just 1 cross, it is just 1 by n matrices, then how difficult can it be to work with the duals? Should it be very difficult? No, it is just these matrices, 1 by n matrices. So it should not be difficult, and that's what we want to understand, right? So this and this is just this. Okay? So right hand side is of course a vector space. You know that if you fix the m and n means fix the dimensions, means the number of rows and number of columns, and take all matrices of that thing, then that thing is obviously a vector space. It's obviously a vector, right? Right. So first, again, I'll use the same style, this phi. Okay, show first that phi is injective and surjective. That is homework, right? Phi is injective and surjective.
We are the files map from F to AF. So AF is
no,
AF is
F goes to AF. It's a map from V star to these matrices.
Okay.
And that's an
okay.
example. Yeah, means that's a instance. Right? So you take a dual, you take a linear functional from V to F, and you send it to the matrix. Obviously, you will go to do different things. Will go to different matrices. All right. So yeah, two different functions will go to different matrices, right? And obviously, every matrix will be achieved, right? Yeah, that so those two things should come from theory of linear transformations, which have okay, but have you done linear transformations?
I did, but not
Not
vastly.
okay, okay. Then let's check it. Otherwise, it's not good. Let's check. Let's check it. So let's first check phi is. Uh, I mean, it's even easier, but yeah. But let's just check it direct like this only. So phi is injected. Phi is injected. Yeah. So I, okay, can you just give an inverse? Can you just give an inverse directly? Then job will be done. We don't have to do anything. You just give an inverse, right? So it's very easy because you have told me how to construct the matrix, right? So we should be able to give an inverse. So let me see. So you're just taking a matrix on the right hand side, and I'll give you an inverse. So what's the candidate of inverse? I will map it to a function g, right? And I will define g like this. Okay? So g of bi, I'll define as ai. This will
E
be my
of
g.
B. Okay, okay.
It's okay, right? So I am defining. So far, I am not claiming anything. I'm just defining a map from this side to this side, which I know will be an inverse, which you can feel it will be an inverse, and then we'll prove that it's an inverse. Okay. So you see, if you take a1 up to a, and where should you send it? What should be the linear transform? What should be the function from v to f? It should be this function where you should send it, right? Which take bi, which is the ith basis, ith element of the basis, to where? Ai. You remember af was what? If you recall af, then there is no question.
F of A1, F of, yeah.
So I am doing that only. I mean, sorry, b1, f of b1, f of b. B was the basis, right?
Yes,
तो
yes, yes.
तो हम लोग सब बेसिस एलिमेंट्स का आउटपुट लिख रहे हैं, तो यहाँ पे आउटपुट दिया हुआ, हम लोग को फंक्शन बनाना है, तो आउटपुट्स आर दीज ऑन बी आईज, that will be the function, right? That's it. And then you just compose and check that this is inverse of each other. That you can do.
हमको लाइक ए के ऊपर इनवर्स बैठा फंक्शन बैठाना नहीं है जिससे हमको पिछला वाला एफ मिल जाए, मतलब बी मिल जाए, लाइक एफ इनवर्स ऑफ A1 इज B1.
हाँ, that is what I am doing. But मुझे तो तुमको क्या करना है? मुझे यहाँ से एक जनरल एलिमेंट लेके उसका हमको दिखाना है कि वो कहाँ पे जाएगा. I cannot just take something from the image and tell you where it is going to go back. Right? I don't even know if it is surjective at the moment. I'm trying to prove both the things at the same time. Right? So you imagine if you have two sets A to B and you have function f, right? If you want to show this is bijective, you have to just construct an inverse, right? So for every B, you have to tell me where it is going. You want to construct a G. Okay, that G and this G is confusing maybe, but yeah, whatever H. You see the point? Capital F, capital H, capital G, right? तो हमको कैपिटल जी बनाना है, तो कैपिटल जी बनाना है मतलब इट विल बी अ फंक्शन फ्रॉम बी. तो मुझे बी से एक आर्बिट्री एलिमेंट बी उठा के आई हैव टू टेल यू द रूल वेयर इट गोज इन ए, राइट?
ओके.
That has to be that cannot depend कि मैं इमेज से एक एलिमेंट उठा के I show you where it goes. No, then it will not be bijection. Then it will not be a function from B. It will be a function from the image of F, which is in B, but I need to show a function from all of B. Correct? So that is just plain set theory, right? Yeah, exactly. So you can ponder over this, and then you see that this is done. That phi is bijection. But you have to show phi compose size identity, psi compose phi. The both you have to show. Otherwise, it's not done, right? Otherwise, it will not. If we one side inverse दिखाने से it will not work to show both in. Well, one side inverse works because of some reasons, but in this case, we cannot say all that. I mean, so far, we can. So phi is bijective. That was some very simple, straightforward thing. Okay, now you have to just check that if you take phi, this thing, and if you take two functions f and g, then this will just be this. And this I will
okay.
leave for homework. Okay,
Okay.
you have to just show. कि f plus g का जो मैट्रिक्स होगा वो ये दोनों मैट्रिक्स का सम होगा, f का मैट्रिक्स और g का. You just write the matrix of f plus g, write the matrix of this, write the matrix of this, and just see for yourself. It will be equal. Okay. Yeah. So yeah, obviously you have to use the linearity. Okay, let's write it. So इसका matrix क्या हो? What is this? Is a matrix, right? So what is this matrix? This matrix is f plus g of b1. So it this doesn't need anything. This doesn't even need the fact that what I'm trying to say. This doesn't need the fact that f is linear. It is always f plus g b1. Phi of f plus g I'm writing. Okay, this is f plus g this and right. This is by definition, right? Once you have the definition, there's nothing to do. This, and now you break it. It will be the right hand side, right? Just write it. It's very, but you should just write it. You know, writing is very important. Then you will just gain the confidence. And so this is it. This is a very simple thing. And the third is that this is also simple. You see, if f is in this space, then 2 times f is in that space, right? Root 2 times f is in that space. We understand what those things mean.
No, sorry, root 2.
Sorry, so root 2 is probably wrong. So if f is there, if f is in this, it's a vector space, right? So if f is there, then lambda times f is also there because you have agreed it's a vector space. Right?
Yeah.
And you understand what lambda times f means. It's just multiplying a function by a scalar, so that you can that you know. And so basically, this thing is lambda times this. That also is easy.
Yes.
So this is a vector space homomorphism, right? Linear. This is the definition of a linear transformation. Because these two are vector spaces. Obviously, the vector space itself is a collection of linear transformations, but that is fine. It's a vector space, right? And this is also a vector space. And we have given a linear transformation from one to the other, and that is a bijective linear transformation, right? Or vector space isomorphism. This is called a vector space isomorphism. Okay. So these two vector spaces are isomorphic. There is absolutely no telling. There is no difference. As abstract vector spaces, there is no difference. Okay. So now you see, so what is the dimension? So what is the answer to question 1? N.
Okay, so n ही होगा लग रहा है. I mean,
Yeah,
if
because
bijective है तो
yeah, bijective and it's a vector space isomorphism means that it's a vector space. They are equal as vector space.
and there is n terms in M1 cross n f. So
Uska dimension is n that you know because this is just this is nothing but fn, right? That all that you know, and uska dimension is n. That is you can see. Now I am not saying that you know the proof of that because that proof is actually not so simple. That to show that the dimension of Rn is n is not so simple. But we assume that. I mean that's a black. Take it as a tool, right? And with that it's n, right? Obviously we have to assume something. One can prove it, but you would have done in your course, but maybe you don't remember it right now, but it's fine. Assuming that it is. Okay. So that question is sorted out. If the dimension is n as expected, what will be a good basis? Question. What is a good basis? So if you are given B B is given, right? B we are not really distinguishing. If B is given, then what should be a good basis of B star? So you know that it has a basis which has n things, right? That is because you have a vector space isomorphism. So here you are assuming two things. One is that if you have a vector space isomorphism between two vector spaces, and here one of vector space is V star, another vector space is Mn, this thing. Vector space isomorphism means that their dimension will be same. That you are, maybe you have not proved it, you are assuming. It's fine. That is not a problem. It's a standard theorem. Okay? And you're also assuming the dimension of the right hand side is n, which is also a very, very standard fact. So these two things assume karke is we are doing. We are standing on the shoulders of giants. Right? These results were proved, but we are now using them, and so it's okay. Now, what is a good basis? Let's answer this question. So, and then the geometry intuition part, that hyperplane part is there, and double dual, but maybe we'll do that next day. But here, let us just understand what is a good basis. So, well, now it's very simple, right? Good basis. So, how will you define a good basis? Well, you use a good basis of right hand side. What else are you going to do? Right? You take the good,
1 0.
right? So, if you take one of the good bases, which is 1 0 0 0. So, tell me the inverse image of that. Where does it go? Or just what is it associated to on this side? Well, it is just associated to I don't know, write it like this. I will. So what is this function? If it goes to g, then what is g? Well, g is a function which takes b1 to 1 and it takes bi to 0 where I is not equal.
Yes.
You know, right? So these are this and these functions is what we are interested in. These functions, right? So let's call this g1. Let's call this g1, right? And so you have this g1, g2, gn. This will be a basis. These will
Okay.
this is a good basis.
So there we will tell write it as delta I, where
Right. So gi,
del
yes.
wait, GIBI equal to FIJ,
gi bj
GI
bj
GIBJ.
is delta. This is the delta you were saying.
That is equal to 1 when I equal to J, and
Yes, yes,
not equal to
yes.
when I know.
Right. So this will be a basis because it's the image of a basis under an isomorphism. So it's a basis. Right? And this basis is a nice basis with respect to this basis B. Okay.
Yes.
So right, that's it. And so this is the basis that you're looking for. It's such a nice basis, very cool basis. And you started with this basis and you got this basis. But of course, this thing lives inside V star and this thing lives inside V. Okay. And obviously, I mean, this thing is actually isomorph. This is in V basically. This is basically V because V is n-dimensional space. It's same as V, right? So you also see that V and V star are isomorphic.
Yes, yes.
That is there, right? And but the main thing is here is the good basis. So when you have B1 up to Bn is in V, then you get this thing, and which is the definition I've already written here. It takes the ith one, takes the ith basis to 1, and it takes others to 0. Just the most easiest thing, nothing. This thing. This thing is called a dual basis. That's the definition. This is the standard definition.
The basis of dual space is called dual spaces.
Sorry?
The basis of the dual space is called dual basis.
But it is dual with respect to the vector space has many bases. This is dual with respect to the basis B.
Yes.
If you change that, it will change. These functions will change. Yeah. Right? Good. So given this basis B, we get the dual basis. This is the dual basis. And usually in the books, they will write it as slightly confusing maybe, but not confusing maybe. I don't know. They write it like this sometimes. Right? or they can also write it as star. All these are just notations. Okay, just to remind you. But remember, these are functions. These are functions on V.
Yes.
So this is the sort of the story. Story goes on a little bit, but there's not much matter left. Not much new thing. Try to read gradually. Then these concepts become more interesting in infinite dimensional space. In finite dimensional spaces, is you see V and V star are same after you fix the basis. There are a few things to understand, which we will try maybe next time if you want. If you have a map from V to V, maybe after you little bit more linear algebra, V to V, you have a map, then you write a matrix for it. And just before you were talking about transpose, so you write a map from V to V, and you take a basis. So you write a matrix for it. It will be n by n matrix, square matrix. Then, given that transformation from V to V, you can get a transformation from V star to V star. It's called the dual transformation. So you have dual basis, dual vector space. The transformation का भी dual होता है. Okay. Take the dual transformation. Uska matrix, if you write with respect to the dual basis, then that will be transpose. The matrix will be transpose of the original. Okay.
The matrix will
become transpose of the original. Okay. And that is true. Yeah. It doesn't need orthogonal basis. Then we can talk about orthogonal basis ka connection with this. But you can see in your book, and if you have some specific questions from your book, you can ask. Then you can understand the theory of the book. You'll feel satisfied, right? Because you're reading something and you're getting stuck, so it's better you clear that up. Then that's first thing is important, right? Then you'll feel like you have covered that. Otherwise it becomes too different. Okay, so let's stop here. Okay, meet on Sunday.
Okay, but I have a little more question that
okay,
the phi is bijective and I'm not getting how to make the inverse function.
Which phi?
The phi from V star to M1 cross M F. Do we just?
No, I constructed the inverse, right? I told you the G.
Yeah,
I constructed the G. So what is G? What is G? G is that, okay, I did not say that properly. The G is that, G is, I'm defining G like this, where G of Bi is equal to Ai. Okay. So G is defined on Bi in this way. And then how will you define G on an arbitrary vector?
So G of B equal to
so
1.
Use the G of Bi is Ai, not 1. G of Bi is Ai, right? So I've defined it on the basis. If I've defined this linear transformation on the basis, I should be able to define it everywhere. And that, you see, this is easy. So Vi is written like this, summation Ci Bi, because V is written like this because Bi is the basis. And then you define this just as you should. Right?
Okay.
Right. You see, I mean, this is what you have to do, right? There is no other thing to do here. So
that's okay, but here we are just sending the G of Bi to Ai. We don't know that Bi will go to Ai. I mean,
we don't know because we are defining. We are defining. No, this is the definition. This is up to us. We can define anything we want. It is just a definition, right? Okay.
So we are constructing like that the ith element will go to the ith element.
Yeah.
Okay.
Yeah. Think about it. Okay, the meeting is going to end. This is the thing, and then you can just check that it's an inverse. Yeah.
Okay.
That is where F comes from. If you look at AF, that's how it comes from. So I'll just reverse the process. All right. See you on Sunday then.